All right, we are starting into Unit 3, Energy, Work, and Power. We're going to spend some time in this video looking at the definition of energy, essential question, as well as getting into some of the types of energy. And depending how it goes, we may actually look a little bit at work, but we'll see how the time treats us. Okay, so we're going to start off with there's three separate parts to this unit. Energy and work are very closely tied together. Um, in some ways they're almost the same thing, or in some ways they are the same thing, but we'll refer to both of them later on. We're going to start with energy and then get to work. Power is a little bit separate. It is connected or tied into the two, and it's just a short piece at the very end that we'll bring in for the unit. All right, so we're going to start with an essential question. This is the overarching broad question that helps guide everything we do in the unit, and that we're going to help to answer throughout the entire unit. And that we're going to go below some of the things that we've done in Unit 1 and in Unit 2. So Unit 2 was in many ways foundational below Unit 1 because kinematics looked at the study of motion, how things move. And in Unit 2, we really got into why do things change their motion? Why does the motion of objects change? The answer being forces, of course. And we had a lot of different types of forces, a lot of different situations in which forces caused acceleration, forces affected the motion of an object. We're going to go one step below that. We're going to go to the very bottom of all this and say, what is the ultimate source of all processes in the universe? All right. A very big question indeed that we can answer in a short answer. Um, the source is energy. So the ultimate source is energy allows for everything to happen that happens within the universe. But we have a longer path to take through types of energy and situations or scenarios in which energy allows for things to happen. But before we do that, I'm going to draw a brief just diagram or image that accompanies this question. Um, so I'm going to do a bit of a pyramid if I can get a decent sort of triangle shape going here. And on the top level, we would say that things move. Motion occurs, displacement, velocity, acceleration, all of that. And the reason, right, even though we have to be a little careful with if something has a velocity, it could be that there's no forces acting on it at that moment. It was previously accelerated. But at some point in time, the reason for the motion of that object is that a force acted on it. So to broadly summarize, because forces act, and the bottom layer of all of this is which is possible due to energy. The reason that pushes and pulls, the reason that forces can act is because energy allows for that. In order for you to push or pull something, and we'll talk about this with the definition as well, you need to have energy so that you can exert forces. And it's no different for everything else within the universe. Energy needs to be there so that forces can act. And then as a result of forces acting, there can be those changes in motion that we observe um, for objects. All right. So let's get into an official definition of energy here. Energy itself, and both the definition and some of the types of energy we're going to talk about would be if you watched there was a video we may have watched in class where a YouTube content creator by the name of Ali Astrocyte was going through some types of energy. And whether or not you watched that video, we're going to go through some of the types that she mentioned. And so there's some good connections there. And also, one of her definitions from the video is for energy itself. So we're going to call energy the ability to do work. Now, this doesn't really suffice for the time being because we don't know what work is. We haven't defined work. We haven't really talked about it. So, before we head over to talk about work, which we'll do later, we're first just going to redefine what that means when we say it's the ability to do work. So, it's the ability to do work or the ability to exert force and cause change. The reason forces are able to be exerted is because of energy. Energy is this ability to then exert force and cause changes. This is not the same thing as force, right? Force and energy are not the same. Um, Energy allows for force to be exerted, but is not the same thing as force. So we'll add that clarification here. Energy allows for these forces to happen, but force as a vector is not equal or the same thing as energy, which is actually a scalar. We do use E for energy in general, which is nice. Makes sense with like F for force, right? E for energy. It's a scalar value. It's not a vector. It doesn't have direction, and it is not the same thing as energy. So even though we're going to get into things like gravitational energy versus gravitational force, we don't want to we want to try to avoid mixing those up, right? So when you're talking about a situation, it will be important to remember, hey, am I talking about the push or pull here? If I am, I would say gravitational force. Or am I talking about the energy that is present, which allows for that gravitational force to be exerted? If I'm talking about the energy, I should say gravitational energy versus gravitational force or force of gravity. So just be careful with that because people will tend to mix the two together, and we don't want to do that. They are not the same thing. Energy is the reason that forces are acting. Okay, well let's get into some types of energy. So again, in class, we may have already kind of brainstormed lists or talked about some of the types of forces that exist in the world around us or with throughout the universe. Many of these, like electromagnetic energy or nuclear energy or solar energy or heat. We'll get a little bit into heat, sort of, but a lot of them we're not going to spend a lot of time with. We don't go into any atomic nuclear type energy here. We're saving that for other physics classes. We're just going to look at some other ones, and we're going to start with potential energy. Find a good color here. All right, so potential energy I'll capitalize it. This is stored energy within an object or system based on the object and its surrounding environment. So this is something like if we watched, there was a video that we might have watched in class prior to this that had like holding back a rubber band or pulling back a rubber band. The fact that it's stretched and that there would be stored energy within it is based on the environment and the surrounding environment being the person pulling back the rubber band. Versus if it wasn't pulled back, it wouldn't have that stored energy within it. Um, so there are two subtypes of potential energy. We'll go through the variable and the units real quick for this as well. So the variable is actually a capital U. We don't use P for potential energy. That is going to come up later with power. So P, capital P will stand for power. Um, some physicists do PE, like capital P, capital E. That can work too. But for whatever reason, sometimes the variables make sense, and sometimes, well, again, power got the priority for using capital P, and we try not to double up too much on using the same variable for two different things because that would be confusing. So they stuck with U. So capital U stands for potential energy, and the units for this are joules. In fact, every type of energy that we work with will be measured in joules. Use a capital J for that. There's a few different ways to write joules, and as we get through some of the equations, we might mention what those ways are to write out the units of joules. Okay, but that's basics of potential energy. Let's move on to two subtypes of potential. So one of those is, move this down here. There we go. One of those is potential gravitational. So there can be stored energy within a system based on the height above the ground. So we'll get to that first. And again, every time we go through these types of energy, we want to go back to that definition to say this energy, this type of energy that's present, is allowing for some force to act. It gives the ability for a force to be exerted and for change to happen. So gravitational potential energy. We're going to get a little bit specific with this definition. We'll talk about some of the keywords that we're going to bring in here. So, gravitational potential energy is stored energy in a system based on an object's location relative, and with this, I'm going to specify also height. Height is a little bit of a weird word here because we'll talk about how something could be below or above a certain location. And also, sometimes we'll go into like planets and satellites and moons and things, and height above the planet could still be a consideration for like a moon orbiting it. But sometimes that, yeah, there's some scenarios in which height doesn't do the best job summarizing what we're looking for. But really, for the vast majority of problems, it is just like how high is this object relative to a chosen horizontal zero line. We can abbreviate that HZL if you want to refer to a horizontal zero line without writing out that entire phrase. We are going to talk about real quick what that is because it's not something we've introduced before. So I'm going to draw like a little cliff with bottom of the cliff. And I'm also going to add in like a pit or a hole somewhere below. Okay, so if our object were on top of this cliff, we had the object up here, and it had some mass m, and we chose to say, well, the ground could be considered zero. Okay, so we'll say that the height of zero is the ground. What we're doing by that is we're defining a horizontal zero line. We're saying anywhere at ground level, anywhere like this purple dotted line, that's going to be where our height, or we're going to define it as like a delta y, is equal to zero. And that is your horizontal zero line. It's a spot we've chosen to say anything above this or below this height will be appropriately positive or negative in terms of displacements. And we'll talk about that in a second. But that's where our zero is, right? And it's if you're sitting on the second floor of your house, you might say, oh, the ground or the floor of my room is zero. But then if you go outside or downstairs and you walk out onto the sidewalk, now you'd probably consider that to be zero. So the reason that we establish horizontal zero lines or choose them is because there's not, especially when you consider the fact that the earth is round, right? Even the ground outside, the physical earth or the ground below us, it varies in height and there's different like there's enough differences that it becomes hard to say what is, something like sea level. It's like, okay, we have a pretty good sense of sea level being a reference point for something. And that's the idea of the horizontal zero line is you're establishing something within a problem to say, I'm going to treat this spot as where the displacement or height is zero. Okay, now we're going to look at a few options. We're going to say if we have an object on the ground, or if we have an object down here. But we'll start with the one up at the top. So if our object is sitting up on top of the cliff, we could draw the displacement from our object to the horizontal zero line. And that would be a negative delta y. Whatever number that is from the object, assuming, and we'll write this in here, assuming that up is positive and down is negative, which is a pretty common choice of directions that we have. Okay, so our object, which is above the ground or at some height above the horizontal zero line, would have a displacement delta y that is negative from the object to that line. Likewise, the one that's sitting below here would have some delta y from the object to that horizontal zero line that would be a positive delta y. Now, to really unpack how this affects energy and the energy of the object, we're going to need the equation for gravitational potential energy, which we will introduce here. So we'll come back to this image in just a second once we get that established. The variable is capital U with a subscript G, gravitational potential energy. And the units are joules. And when it comes to finding how much gravitational potential energy exists for a system, and I'm going to make a quick note on that system side of things up here. The system for gravitational potential energy needs to involve two things. It needs to involve the object, at the very least, whatever object we're dealing with, like the mass in our image over here. And the other thing is the Earth. This gets a little weird when we talk about, we'll get to like open and closed systems and we'll talk about what those mean and we'll bring in potential energy in light of that. But basically, if you have a system that includes both the object and the Earth itself, then you can have gravitational potential energy in that system. We'll end up having to be careful because if we have a system where the Earth is not included as one of the things in that system, which is a little different from Unit 2, where we just had some objects that were like, oh, we tied these objects together. It's an Atwood's machine. So That's our system. And we didn't really include anything like the Earth in our systems for Unit 2. Here it's going to be pretty important what we're including, and the Earth will be one of the things that could be part of our system. The reason being, for gravitational potential energy, you need to look at the interaction between the Earth, which is providing the gravity or has the ability to pull with a force on that object to possibly change what's happening to it. And then you have to look at the object itself. So both the object and the Earth are important parts of that. Okay, so our equation for gravitational potential energy looks like this. There are three things that affect or that we can use to find how much gravitational potential energy exists within an object Earth system. Or it could be like if you were on a different planet, it could be an object planet system of whatever planet you're on. Whatever is providing the gravitational force and providing the gravitational energy that allows for that force to be exerted. So UG, and all of these things are going to look familiar. We're not going to introduce any new variables. The mass of the object is 1, and that's a direct relationship, meaning if you get a bigger mass, there's going to be more potential energy. Then that's multiplied by G, which makes sense here because we have gravitational potential energy. So the acceleration of gravity, or we also call this the gravitational field strength, another term for G. Both of those are written on your equation sheet. So reminder that 9.8 meters per second squared is the acceleration of gravity. And if you talk about it with field strength, the units are newtons over meters, newtons over kilograms, rather, which are the same units as meters per second squared. So they are identical. 9.8 meters per second squared and 9.8 newtons per kilogram are the same units because the field strength, newtons over kilograms, is just measuring how much force per unit of mass will this experience. And so they come out to the same thing. So whether you think about this as acceleration of gravity, 9.8 meters per second squared, or gravitational field strength, and it's already, this is looking like, so far, it looks exactly like our force of gravity equation. But this is a reminder that force and energy are not the same thing. We're not stopping here. It's not just mass times 10 or 9.8. So we're not going to just use the same equation we did for force of gravity. There's also a delta y. So it matters not only what the mass of the object is and not only what the gravitational field strength or acceleration of gravity is, it also matters where that object is located relative to our horizontal zero line. Okay, so let's go back to this image now, and we could note a couple things. This equation does have two vectors in it, and they're going to result in a scalar. So a scalar value, we don't assign it a direction. However, this is one of the few scalars that can actually be negative, and we'll talk about why that is. So mass can't be negative. We can't have negative mass of an object or a system. Time can't be negative, right? We can't go backwards in time or get to negative time or anything like that. Time is only positive. But energy, specifically gravitational potential energy, has the potential, no pun intended, to be a negative value. So let's break that down with our little image over here. Let's take the mass on top of the cliff, and I'll write the energy values in green here. So the mass on top of the cliff has a positive mass, because mass is always positive. G would be negative 10, because we've chosen down to be negative. So that vector G would be negative. And then delta Y is also negative. So for the object on top of the cliff, we'd have a positive mass in the equation times a negative G, 10 meters per second squared, times a negative delta Y. All the negative signs would cancel out for those last two vectors, and you would have a positive amount of gravitational potential energy. So up here, we've got a positive UG. Now, for the one sitting on the ground, delta Y is 0, so there's no gravitational potential energy here for this object. And for the one below, this is where it gets a little weird. Mass is still positive, right? The acceleration of gravity, or gravitational field strength is still negative because it's downwards, so negative 9.8 or negative 10. But delta y for the object below the horizontal zero line, delta y is positive. So in our equation, if we plug in a positive mass for the object with a negative g and then a positive delta y, the number we get will be negative. So you do actually have, in this case, with an object below the horizontal zero line, you have a negative gravitational potential energy. So what does that actually mean? Well, if energy is the ability to exert force and cause change, let's look at the object on top of the cliff. The Earth, with its pull of gravity, has a high amount of or some amount of potential to exert a force of gravity on this object. And if it were to like roll off the cliff or we dropped it off the edge, there could be change that happens. Namely, the object starts from zero velocity, it then accelerates due to gravity if you drop it, and that force of gravity would cause it to speed up faster and faster. The object undergoes change, it undergoes acceleration because of that force of gravity. So there is a potential for the object when it's dropped to fall to the ground due to gravity, due to the force of gravity, because it has this stored energy, right? The energy means there's an ability for gravitational force to be exerted and for change to happen. The object on the ground has no ability for the force of gravity to cause change for that object, right? Relative to this horizontal zero line. So the force of gravity can't cause this object to change in any way relative to the horizontal zero line when it's on the ground because it's already at the horizontal zero line. So we could think of it as there's no way for gravity to cause the object to like get to the horizontal zero line. So there's just no energy present here. For this object, however, not only is there no way for this object at the bottom of the hole to go up to the horizontal zero line due to gravity, right? Gravity is never going to act upwards. That's just not going to happen. So the gravity of the Earth, the force of gravity, will never cause this object from the bottom here to go up to the horizontal zero line. In fact, not only that, but you as a person, if you wanted to lift the object out of the hole, you would actually have to put energy into this, and you'd have to use your own energy just to get it from the bottom of the hole to the horizontal zero line to lift it up against gravity, working against that force of gravity. So this one at the bottom means the negative energy is just kind of a weird thing to see, but what it means is not only is the object at the bottom of the hole not going to go from there to the horizontal zero line due to gravity, that's not going to happen. But also, you would have to actually use your own energy. It requires some additional energy input there with your own force, like your applied force, to bring it up to the horizontal zero line. So, again, running through them from first to last, we'd say this one has a potential due to the force of gravity. If it were like dropped off or rolled off the cliff, it has the potential to, because of the force of gravity, to move from here to the horizontal zero line to experience that change. For the one on the ground, there is no potential for it to do that. It's already at the horizontal zero line. The gravity is not going to cause it to go to the horizontal zero line. It's already there. There's no change that would happen there. This one, if we wanted some form of change or if we wanted to move this object to the horizontal zero line, not only is there no potential for gravity to do that, it would require some additional input or additional force from a person or whatever lifts it up to the horizontal zero line. Okay, so that's kind of my summary of based on where you choose zero to be, almost all the time we will have positive gravitational potential energy because we very rarely are ending up dealing with a horizontal zero line that has an object below it. But if that ever comes up, and it may in a couple problems, it may occasionally be a thing, then we would have negative gravitational potential energy. And if we're just on the ground or at the height of zero, then there's no gravitational potential energy at that spot, right? So thinking about it as, is there the potential for this stored energy in a system to then allow for or have this ability to exert a force and cause change? So gravity only has the ability to exert force and cause change, when we have this object that is somewhere above the chosen horizontal zero line. If it's at the zero line or it's below it, then you have either zero or negative gravitational potential energy. Great, and that's UG. So one of our two types. The second is spring or elastic potential energy. Let's get through that. Okay. And this is basically what it sounds like, which is the energy stored within a stretched or compressed spring or some other elastic material. So this could be like a rubber band that's been stretched or something that holds or stores that energy. Most of the time for our problems, we're really just going to be dealing with springs. Um, so yeah, when you stretch or compress a spring, it has stored energy within it. Unlike the gravitational potential energy, we don't need an object Earth system. We don't need multiple things within the system to have this type of energy because gravitational really depends on, okay, what's the object providing like the force of gravity and the energy, gravitational potential energy? That'd be like the Earth itself. And then relative to the Earth or the chosen horizontal zero line, where is the object located? So that's why object Earth system becomes important for UG, for gravitational potential. But with a spring, all you need is a spring, and as soon as that spring becomes itself stretched or compressed, you then have stored energy within it. All right, let's go through this one. So the variable is US, U subscript S for spring potential energy. You could also do U with a subscript ELAS. You might, I'll throw it in there. You might occasionally see that. It's not going to come up a whole lot. So um, you could have elastic if you had an object like a rubber band that was like not technically a spring, but you wanted to look at the energy stored within it, then we could write it as U elastic or U ELAS. But you won't see that a whole lot. Now the units are the same, still joules, and we have an equation for uh, spring potential energy. It looks like this. Your equation for spring potential energy is equal to 1/2 times the K value, and we should be pretty fresh off of unit 2 to know that that's the strength of the spring. That's simply like how strong or weak the spring is. So 1/2 times the K value times delta X squared. So a couple things to talk about. The strength of the spring does affect how much stored energy there is. If you have a stronger spring with a bigger K value, you're going to get more stored energy when you stretch it a certain amount. But the thing that really, really affects the amount of stored energy in a spring is how far you stretch or compress it. And a couple things with the squared here. K is a positive number, even though in our spring force equation, right? This is where this gets really important. In our spring force equation, we had negative K delta X. But that negative was not to indicate that K itself is negative. Instead, there was just a negative sign in front of it. So in the spring force equation, not to be confused with spring energy, right? Because we don't want to start thinking they're the same thing. It's tough because we've got gravitational force and gravitational energy, spring force and spring energy, but they are not the same thing. They don't have the same equation. even though they have some similar variables here. So negative k delta x was like -1 times the k value times delta x. Now there's no negatives in here. Even though delta x could be negative, if you compress your spring to the left, with left being negative, you'd have a negative delta x. However, that is getting squared. So even if your delta x is negative, the fact that it's squared means spring potential energy will always just be positive. And going back to the idea of positive and negative energy up here, what that means is your spring, when you stretch or compress it, always has the potential to exert a force and cause change. Unlike the object sitting in the pit below ground level, where there's not only is there no potential for gravity to like move it to the horizontal zero line, you'd actually have to get something else to put energy into this and move it to the HZL. With springs, anytime you stretch or compress them, there is the ability to exert force and cause change, right? A stretched spring can exert some force and cause an acceleration. A compressed spring can do the same. So that's a couple things with that equation is you're not going to run into negative spring energy. It's just always going to be positive. Yeah, there's that. But spring energy is fairly straightforward. I mean, once we start doing graphs of it and graphing, we'll have to note the fact that we've got that sort of squared relationship of spring potential energy and then delta x squared. So it's not going to be like a straight line sort of graph when we do energy graphs. So we'll have to keep some of those things in mind, of course. And don't forget to square that delta x when you're doing any sort of math. It could also be a delta y. If the spring was stretched vertically or compressed vertically, you could just swap in a delta y and it would work just as well as a delta x for displacement. And just remember, we should know this from Unit 2, but remember that displacement is the difference between the natural length of the spring and the stretched or compressed length. It's how far you changed the length of the spring by. Okay, and that's potential energy. There are other types, of course. There's nuclear potential energy stored within the nucleus of atoms. There's molecular potential energy. There's chemical potential is what we call that because the bonds between molecules, we have stored chemical potential energy that could be released through a chemical reaction or like burning wood on a fire is releasing chemical energy, all kinds of things. But we're not going to get into any of those because we're not doing chemistry things. We're not getting into atomic physics or nuclear physics or anything like that. So we're actually just going to end up with the two types of potential energy. Potential stored energy due to gravity based on an object's height or location relative to horizontal zero line, and spring or elastic potential that is stored within a stretched or compressed spring or other elastic material. Okay, so there's all this stored energy, right? Springs that are stretched and compressed, objects that are like above the ground or ready to fall, could fall from their location, or could experience a force of gravity that causes something to change. All this stored energy is not the only type. In fact, when objects begin to move, we're going to introduce kinetic energy. So the other important type to mention here is kinetic energy. So this is energy that is present for a moving object. That's a pretty straightforward definition. There's nothing, if an object's moving, it has kinetic energy. That's it. We'll talk about the equation and kind of what goes into that and how to find that amount of energy and all that. But yeah, if something is moving, it has kinetic energy. And these are not exclusive. Sometimes people might think, oh, we either have potential or kinetic. Well, we could disprove that pretty quickly with our gravity example. If the object falls off the cliff halfway down, it still has some height above the ground. It still has some delta y down to the horizontal zero line. So there would still be some amount of potential energy. There'd be some stored energy that could still allow for force to be exerted and change to happen with the force of gravity. But it would also be moving halfway down the cliff as it's falling. It would have kinetic energy. So these are not exclusive, like you can only have kinetic or only potential. But anytime an object is at rest, it doesn't have kinetic energy. It could have potential energy, the system or the object, um, or specifically a spring, if we're looking at springs. But either the Earth object system or the spring could have potential energy. But if something's moving, then it certainly has kinetic energy. Okay, let's do units and variables and all that. Variable is K. K for kinetic. Capital K, not to be confused with lowercase. Lowercase is the spring constant that we just used in the spring energy equation. So, yeah, K for kinetic energy. All right, the units are also joules. All of our energy types will be measured in joules, just like all of our forces were measured in newtons. And remember, they are not the same thing. In fact, once we finish this, we'll talk about the units using these equations. We'll talk about what the units are for joules. All right, the equation is as follows. There's two main things we look at for determining the amount of kinetic energy present for a moving object. So K equals 1/2 times the mass of an object. So kind of like our gravitational potential up there. It does matter if you've got a big object or a massive object moving, then that will have more kinetic energy than something with less mass that's moving the same velocity. So velocity is the other piece of this. And it's v squared. So very similar to the last one we looked at, 1/2 times a variable times a different variable squared. Not the same ones, right? K and delta x for spring force are definitely different from the mass and the velocity. So uh, the more mass an object has, the more kinetic energy it has if it's moving. And then you get, I mean, you also have velocity in there, and velocity plays a bigger role in that if you have a 1 kilogram and a 2 kilogram object both moving at 1 meter per second, yeah, the one with 2 kilograms has twice the kinetic energy. But if you double the velocity, so one object goes twice as fast as another, that velocity gets squared in the equation, and you suddenly get 4 times as much kinetic energy if an object's moving twice as fast. That's back to those relationships between variables in the ratio type questions that say this object's moving twice as fast as the other. How much kinetic energy does it have compared to the other object? So, because of the v squared, velocity heavily affects that kinetic energy, and yeah, it's not a direct relationship. If you double the velocity an object moves at, you will quadruple the amount of kinetic energy it has. Last thing with that is kinetic energy also is only positive. Mass is a positive scalar, can't be negative. And even if your velocity is negative, even if your object's moving downwards or left or whatever the negative direction is, it is squared. So when you square that negative number for velocity, the answer for kinetic energy K is going to be positive every time. So we're always going to have positive kinetic energy. Gravitational potential is the only one that can be negative sometimes, but pretty rarely do we have like an object down in a hole that's below the horizontal zero line. All right, let's talk a little bit about units. I'm going to break down with all these equations what the units are. So we'll swap back to blue for units. So joules, I'll put in parentheses here. The units of joules go with energy, and they are equivalent to kilograms for mass times meters per second squared of acceleration times meters of displacement. That would be using the gravitational potential energy equation to say joules are equivalent to kilograms times meters per second squared times meters again. Over here, we've got joules equal to K is measured in newtons per meter times meters squared. Now, how can we show that those are the same thing? Well, the meters cancel out here, so it's newtons times meters is because one of the meters goes away. So that is equivalent to, well, a newton is a kilogram times meter per second squared, because force is mass times acceleration. So newtons are kilograms times meters per second squared. And then we take that, newtons, and we multiply it times meters. And we get to exactly the same units as we did up here. So that's another way you could write joules, is you could say joules are newtons, well, newtons over meters times meters squared. But simplifying that, joules are newtons times meters. That's going to be important when we talk about work, because work will also be joules, and it's going to deal with force and displacement with newtons and with meters. So that's a couple ways to write it. You could also go over here and say, all right, joules energy, that's equal to kilograms for mass times velocity is meters per second, but we're squaring that, so it'd be meters squared per second squared. And that we can also see is exactly the same thing as what we got above, because you could combine the meters in the numerator, and then you'd have kilograms times meters squared over seconds squared. So all these equations for energy are all equivalent to joules as units go. And a joule is either a kilogram times meters squared per second squared, or you could, with the spring energy equation, you could describe it there as newtons times meters. Yet another reminder then that force and energy are not the same thing. Newtons are the units of force. Newtons times meters are the units of energy. Because when we talk about energy allowing for change to happen, we're going to be bringing in displacement and say, okay, when energy causes a change for an object, we can look at where the object moves or how far it moves. And that displacement will help us when we look at things like work to determine how energy is affecting or changing, or allowing for force to change that object's motion. So energy, again, is the ability for force to act and to cause change. And whether it's potential energy stored within a system ready to be put into some force that could cause change, or maybe it's kinetic energy where an object is moving. And think about that too, right? Moving objects can exert force, have the ability to exert force, because if you throw a dodgeball really hard, then when it hits someone, because it's moving super fast, it will exert a force and cause change. So, yeah, there's that energy piece of being able to exert force, whether it's stored energy that could exert a force or kinetic energy of motion that could exert a force. All right, last type we're going to talk about, we're going to do a subtype of kinetic energy. It's technically the same idea as like motion, moving, energy due to motion. We're going to do a subtype of kinetic, and we're going to say thermal energy. When we say thermal in physics, there's two main things we're going to refer to. One is heat, right? Heat, like thermal energy, or sound is also thermal energy. And both of these are due to small scale motion of particles. Okay, so think about like heating water up. There's water sitting on the stove in a pot, and that water, the molecules themselves are moving around. There's small scale motion. They're like vibrating and moving and going back and forth to some degree. If you freeze that water into ice, there's going to be less motion of particles. And the more you heat it up, the water being warm or hot or even boiling means that those particles are moving faster and faster and faster. So when we get a lot of heat energy, that's because there's a lot of motion on a small scale of those particles like the molecules right in the water. Sound is actually the same thing. If there's no sound, right, if it's like still and quiet and you don't hear anything in the air, that means that the air molecules are, I mean, they're moving. They are moving, but they're not moving in a way that your eardrums will pick up sound, versus as soon as I like speak into the microphone and you hear it coming out of your speakers or your headphones, or we're in class and your friend is explaining something to you and you're hearing the words that they say, that sound is small scale motion of air particles that our vocal cords are causing compressed packets of air, right? So we're manipulating or causing the motion of air particles to travel through the air in sound waves of sort of bunched up particles. And it's weirder the more you think about it while you're speaking or listening to something. But um, that small scale motion of particles is then picked up by your eardrum as how fast are these various molecules of air moving when they hit my eardrum. And that's the whole idea of sound, right? If something, you can picture it as if something falls and hits the ground and makes a loud sound, there's a sudden burst of motion in those air molecules and the particles of the air that then travels in a wave through the air of the fast moving air molecules and then um, reaches your eardrums, which is why really loud sounds can actually damage them, right? Because if you picture the air molecules and particles moving really fast for an incredibly loud sound, when they hit your eardrums, that high energy and high motion, large amount of motion of the particles when it's a really loud sound can damage your eardrums. Anyways, all that to say, we don't do a ton with thermal energy. We'll mention it from time to time. Um, we'll talk about friction. Friction produces heat or sound. That's a big one for thermal. The variable we're going to use, we're actually going to use E for energy, and we're going to do a subscript TH. So thermal energy. There we go. And then units are still joules. Okay. And the equation, so part of the problem with thermal energy is that it's mostly due to drag and friction, which makes it tricky because we don't like the equations for drag and friction, and they're a little tricky. We don't like to deal with them. The other is just we have another way to find it, but we're going to eventually use something like work equations, which we haven't looked at yet, but we will eventually, or conservation of energy. And I think probably in the next video, we'll at least talk about work and possibly we'll get to conservation of energy. Um, so both those things we'll get to. But thermal energy, yeah, we don't really have its own equation to look at how much heat or sound is produced by something like friction. Um, yeah, we just tend to use the work equation. The work equation is a very, very good way to do this, as well as using conservation of energy. We can find how much heat or sound was produced during a process. So there's a couple options there, but it doesn't get its own equation like kinetic or the potential energies. All right, so to summarize what we've talked about with energy and individual energy types, we've got a definition of energy that says it's this ability to exert force and cause change. Um, it's also the reason for everything that happens throughout the universe. The reason that any given process occurs is because some form of energy, whether potential or kinetic or thermal or something else, um, some form of energy allowed for a force to be exerted, which caused some change, and then a process occurred, right? I randomly thought of this video that I saw, which was like, um, the video was titled like imagery of happiness reaching your brain, and it was the proteins or the this is showing my lack of biology, but the triggers and the chemical reactions that cause happiness or any emotion or thing that's released in your brain, right? The feelings and things that occur. There was this little image of like uh again like a protein or a transmitter or something that was carrying the chemical to the brain, and it was like walking, it was like moving and walking along. So I pictured it as like the energy that exists within your body allows for that force to be exerted, which causes a change in the motion of that chemical that gets carried to your brain, and then you feel happy. So even like the process of being happy or sad is about the energy that exists, which allows for forces to be exerted that like move something from one place to another, cause a change in something, cause some process to occur, and then you feel happy, you feel sad, you lift something, you run, your car engine starts, your cat plays with their toy, whatever it is. All those things require energy so that whatever process occurs, right? Plants growing or a rock falling off of a cliff, all of those are processes that require some amount of energy, allowing for force to be exerted and for that change to happen. So, yeah, chemical, biological, physical processes all require energy. Okay, cool. I think we'll mostly call it there. So yeah, types of energy are going to be important. We're going to look at potential energy, both gravitational and spring, within our systems or situations we encounter. Kinetic energy is going to be important for anything that moves, moving objects, and thermal energy will show up with heat and sound. And just a quick note on like the broad scale of the universe. There's interesting stuff we don't really get into, but we'll talk a bit about with conservation, which is like the amount of available energy in the universe goes from sort of usable forms to unusable forms. So we might mention some in the next video or the next couple videos how um, energy does tend to get sort of spread out or used in that the potential and kinetic energies turn into things like thermal, and we'll talk about how it's a little hard to get that energy back into a usable, more usable form. So, renewable energy as well is an important piece of all this to say, of all these energy types that allow for processes to happen, we do want to be aware of what types of energy we're using and how that affects things too. So interesting thoughts there. Okay, cool. Well, that wraps it up for this video. We'll look at work. So next video, we'll get into work, define what that is, talk about the work equation. There's something called the work energy theorem that looks at changes in energy occurring due to work. We may get into conservation of energy after that and move on through systems and open and closed systems and all kinds of other stuff. Yeah, so this is the basis. This is the foundational basis for understanding the main types of energy we encounter. There's not nearly as many as forces. We had 7 forces. We've only got really 4 main types of energy, and 3 for the most part, because thermal shows up rarely. But it's enough to start working with a lot of the problems and equations and things that we'll encounter. Um, Although there's a lot more groundwork, we gotta get through work. We gotta get through conservation of energy, changes in energy, things like that. So there's a good amount more to do before we really start solving some problems. Okay. Well, don't forget that the Schoology page has a link to anonymous questions through a Padlet. If you have questions about any of this or want to clarify things or just ask about something, if you want to ask about the energy that exists within the universe or whatever your question might be, throw it in there and we can address it in class. And yeah, we'll see you then in class and hope you all have a good rest of your day.